Did Einstein prove Newton wrong? This is one of the questions that comes up in popular science every now and then. And for good reason. When Einstein introduced his theory of relativity in the early 20th century, it became gradually clear that his theory made more accurate predictions about nature than Newtonian mechanics, which had been the leading theory for over 200 years. So, was Newton wrong? And to what extent does relativity improve on Newtonian mechanics? In this video, we'll explore this question by looking at the concept of kinetic energy, and we'll use the Taylor series to compare the results of both theories. Let us first look at what Einstein and Newton have to say about kinetic energy. Consider this rocket of mass m and velocity v. According to Newton, there's a very simple formula for the kinetic energy. K is equal to a half mv squared. However, according to Einstein, things are not that simple, because Einstein knows that strange things can happen once the rocket approaches the speed of light. In fact, if we keep accelerating that rocket, it cannot exceed the speed of light. No matter how much work we do in order to accelerate the rocket, its velocity will eventually stay almost constant and close to the speed of light. But that poses a question. How can kinetic energy increase while the velocity stays constant? According to Einstein, this can only happen if the mass increases with increasing velocity. This mass is called the relativistic mass. It's equal to m over the square root of 1 minus v squared over c squared, where m is the mass when the rocket is at rest, or simply the rest mass. Alright, let's derive an expression for the kinetic energy. Kinetic energy is the energy due to the motion of a moving massive object. So, it must be equal to the energy when the object has a velocity v minus the energy of the object at rest. And using Einstein's famous formula, E is mc squared, we can express the kinetic energy in the following way. You can see that we use the formula for the relativistic mass here. Great, we did it. But unfortunately, this is not a very simple formula. How can we get a better understanding of it? Of course, let's do a Taylor expansion and see what we get. First, let's get rid of the v squared over c squared and call that x. Now, we can expand this around x equals to 0. But before we continue, please pause the video and try to find the first few terms yourself. Okay, is this what you got? Well done! Finally, let's substitute v squared over c squared back and start analyzing our expression. Amazingly, the first term is exactly equal to the kinetic energy of Newton. The other terms can be regarded as relativistic corrections, which will be small when the velocity v is small compared to the speed of light. This can be shown graphically as well. In this plot, you can see how the kinetic energy increases as the velocity increases. The first term of the Taylor series is the Newtonian kinetic energy, shown in the blue curve. For velocities that are much smaller than the speed of light, the blue curve is almost indistinguishable from the red curve. As we keep adding terms, the approximation clearly becomes better for larger velocities as well. And so, we can regard Newton's formula as a Taylor series approximation of Einstein's formula to second order in the velocity. Einstein therefore concludes that Newton's formula is not bad at all, as long as the velocity, of course, is much smaller than the speed of light. But just how good is the approximation? Can we estimate the error for a given velocity v? And for which values of v does the Taylor series converge to the real function in the first place? In class, we will acquire the necessary tool for answering these questions. Hope to see you there.